Draft physics presentation, such. Anyway, so just not a complete video, specific to a specific subject, essentially, magnetism, and the related concept that magnets create. Everybody has these drawings of things moving around magnets, famous kind of, swirly bits, hyperboloids and toroids, and even the conventional physics has this idea of movement, and I see no evidence indicating that there's anything that's actually moving. That's why you have to move the magnet, or you have to move the conductor in the magnetic field to create any noticeable effect between magnets and paramagnetic things, or even ferromagnetic. But certainly to create eddy currents or electricity, you need to move the magnet. That it doesn't have anything, there's no evidence of anything moving. So again, let's do the traditional magnet here, and let's see if I can, should have drawn it higher. But anyway, and the idea is that there's a field. We'll draw it in blue because they don't really indicate much. That's going around the magnet. A wobbly camera isn't a great idea. And so even in the traditional diagrams, they give these field lines the idea of motion, that there's some kind of circulation. Now in the more elaborate ether type people, they end up having these lines swirling around the magnet in some manner or other, and creating a some kind of whatever swirly bits. So they're not only going from one end to the other, but they're doing it in a direction as they go around to create the idea of this hyperboloid thing with these toroids. So it's got stuff going one way at the top, and then it's got stuff going this way around on the sides, and lots of movement. And again, I just argue, is there any experimental evidence indicating any detection ever of a magnet just minding its own business, and any indication of anything moving ever anywhere? I'd say there's none, because these are wrong. Okay, so the first thing I'd point out is these field lines are entirely arbitrary. They're a construct of the fact that when they do these kinds of experiments with, say, iron filings, they create a barrier between the magnet and the little filings. And so the filings can't get to the magnet. They want to just go to the magnet. They want to just flip the right way and go to the magnet. And it's only by artificially separating them from that they create a pattern. And that the lines themselves are just being created because all the little magnets, I'll just make them as lines just to indicate, that it's just the filings. But each little filing is turning into a magnet when it's in the presence of a magnet. And it's aligning exactly opposite to the magnet in the attractive mode. So they all flip to be the north-south, and they go south-north. And they're just arranging based on the strength of the field they're in. And so one in this position would be influenced more by the north side than by the south side, obviously. So it lines up with a little bit of a tilt in that direction. So they're just indicating the strength of the polarization field, and that's all they're indicating of. And what they're doing, essentially, by all lining up in the same way, that is, they're all lining up south-north each one of these little magnets, and they're essentially just creating a big south-north magnet themselves. And each line, okay, so we go a little further out, we have another line of little magnets. Each line is south-north, so they're repelling each other. So this line becomes a magnet, this line becomes a magnet, and their alignment is the same, which means they're repelling each other. And so that's why these lines have a separation. It's just the strength of the repulsion. So they're really quite arbitrary. Now they use another kind of line. These are the ones you see. Okay. Now in the math, they'll use these lines, but they're using them in a synthetic way. They're not actually real lines. They're just using the idea of using lines to illustrate the intensity of the field. So they'll draw, like for charges, they'll draw, like if you had a little charge, they'd put lines around the charge, like topographical lines, indicating the strength of the charge at different locations. And the longer the distance, it means the weaker the charge. And so they'll make lines around magnets to illustrate the strength of the field at different locations. And but those lines are arbitrary. I mean, they're not real. They're synthetic lines. They don't happen in nature. And so these lines just end up representing another set of lines, which would be the actual rays of magnetism. So now we're back to this idea of divergence, and the fact that the divergence indicates field strength at specific locations. So you can understand that at specific distances you'll change the strength, because the size of anything, okay, you can see that this line is only 2 boxes long. This line might be 8 boxes long, and this line might be 10 boxes long. And so that's an indication of the field strength, in the sense of how likely, if a little dot was to fly off in any one of these directions, how likely is it to hit the box? Well, because of the bigger range of possible locations the dot could end up with at a distance, the odds of hitting the box is smaller out here than it would be here, where it would be 50-50. So you'd have a 50-50 chance of hitting the box there, and you'd only have a 1 in 10 chance of hitting it out there. And this is essentially the inverse square law in precise math. But obviously that breaks down when you get really close to a magnet. So it's not a law, it's just a tendency. It's the inverse square tendency, but it's not an absolute law. But anyway, it's essentially describing that fact. So these ray lines, it doesn't matter how many you make. So you can make 20 of them, you can make 50 of them. It doesn't really matter how many you make, as long as you recognize their divergence, and that by percentage they spread by a specific inverse square rule. So half the distance is 4 times the effect. So we're back to the cubic argument, that everything gets 4 times bigger at half the distance. And then you go 3 by 3 for 9. But that's the rule. So that's why magnetism and gravity weaken rather rapidly with distance. So anyway, the idea of these field lines is totally misunderstood, because they're not really creating anything. And what's really happening in a conductor, for example, a piece of metal that's not magnetic by nature, it's not magnetic, it's not magnetic, it's probably the way to say it, okay, and it can only be forced to be magnetic when a field, a magnetic field moves inside of it. And so we'll do the drawing of the magnet. So the real idea to understand about what's happening, well, maybe I'll draw this first. I should have probably made it bigger, but it'll do. So the idea is when there's all this external force coming in, and it's mixed of these two charges. So the charge is really a function of the external force, and the material bits are just filtering that charge effect. And so what's essentially happens is any black force that comes in, say in a direction like perpendicular, it perpendicular to the surface of the magnet, it ends up being diverted and comes out the black end of the magnet. And that's true for whatever direction it comes in. And likewise, if something just goes straight through, the black thing will go through the magnet. And the same thing is happening with the red force. So whether it comes in this side or this side or this side or that side, it will leave the magnet out the end, and creating, in essence, a circumstance where if a red comes in to any part of the red magnet, it reflects. So it can't possibly get out the north end. But if a black comes in the red end, it will travel through the magnet and come out the black end unmolested. So you can sort of get the idea that it just depends on the angle. It has to be perpendicular to the magnet to be bent. If it comes in some other angle, it just goes straight through. And all the red force and all the black force, if the red hits a red, it reflects. If a black hits a black, it reflects. And that's where the magnet gets its strength from. Because when you line up two magnets of the same polarity, they will essentially trap the energy between them, because it will just constantly reflect. The red energy and the black energy will constantly reflect, and any black energy coming this way will end up essentially reflecting. Any red energy coming this way will end up essentially reflecting. So it creates the repulsion, and the absence of that force, reversing it, creates the low pressure where there's no reflections anymore, and the two magnets are pushed by the external force into each other. So what happens when there's a conductor, so the real how magnets should be understood to function is that they are radiant. They're not creating any wave field or any kind of stuff like that. They're radiating force. Okay, and it's all one kind of force coming out of one end, and all the other out of the other end. So one force affects protons in that it will accelerate a proton. It will move it. The other force will affect electrons. So this is essentially the electron end of the magnet, and this is the proton end of the magnet. And so when you have a neutral conductor, what essentially is going to happen is the electrons will tend to be, if you move the magnet just straight in, the force is going to tend to compress electrons at this end. So whatever, say if they were that far apart, they're now going to be much closer to each other because they're being compressed or pushed by the force. And the same is happening on the other end to the protons, which are being compressed by the negative force, and the electrons are essentially being unmolested because it's all red force. So they're essentially expanding at this end. So you can sort of see that it's where the electrons are compressing and where the protons are expanding, and vice versa. So it essentially magnetizes the substance. So the substance was neutral, but because the electrons are being pushed or compressed at this end, it tends to go electron, or north, or however you want to look at that, and the other side tends to go proton heavy. So it ends up being a magnet, essentially, because of that movement. Now, the other trick to the movement is that in moving the electrons, you're creating a current. That's like electricity. And what's really happening with electricity is the electrons are in positions. And essentially, when one gets pushed closer to another one, it creates more reflections between it. So it has a higher pressure. And that higher pressure moves the other electron a little bit. And that little bit of movement creates a higher pressure between these electrons. So essentially the pressure is moved through the chain of electrons. So it's the current isn't really about the electrons actually going like this electron moving to this location. That isn't necessary for electricity to happen. What's really happening is the pressure is moving. So the real movement of the current is really just the movement of the pressure, and that can happen at the speed of the force, essentially, because you're just moving the electrons a little bit. So it might be a little bit slower than the speed of light, but it's pretty close to the speed of light, because what you're really just doing is moving electrons a tiny bit of distance to equalize the pressure. So it's like a spring or some other mechanism. You push one end, it compresses the metal at that end, and the compression moves through the whole spring to the other end. And the speed of that compression moving is faster than the actual well, spring probably isn't a very good example. There's probably better examples of the fact that the pressure moving is happening faster than what it appears to be the speed of the electrons moving. Now, when the pressure gets high enough, the electrons will jump as this process is happening. So some of the electrons will be pushed into new locations, and when they push, they essentially kick this electron out of its position. That electron ends up pushing this electron out of its position, and they just keep cascading that push to pile up more electrons. But the important feature was the pressure that's creating that effect. So the higher the pressure, the more likely you are to move the actual electrons. But the electrons will still only move much slower than the actual speed of the pressure moving through the electrons. So the pressure is what's really doing the moving. So anyway, you could say that the electric current, the movement of the electrons, the compression of them, was what causes essentially the magnetism, because it's caused this compression which changes the balance of exposure to electrons and protons and turns the non-magnetic material into something that's for a moment magnetized. Now when you move the magnet away, all these things go back to their relaxed state. They all go back to their normal state, and then you can repressurize them. But once you've pressurized them, you have to, that's why there has to be alternating current, is because once they're pressurized, if you don't let them relax, you can't move them anymore. They move to a location, they're pressurized, they stay pressurized. So unless you jiggle this magnet to change the pressure, you can't create any more movement in the electrons. And it's that, again, the movement, that little bit of jiggling, that is essentially that tightening of the positions that's creating the effect of the magnetism. Now, I probably need to say more clearly that the actual movement of the electrons involves the creation of the opposite force. So essentially what's happening, I have to be clear on this. Yeah. Okay, yes, it's the expansion of the protons that is creating the turn, the left, because this ends up being an opposite magnet. So I wrote it as EE. This is really going to go PE in terms of the effect. So I should have wrote it this way. Yeah. Okay. So my error. Sorry, it's hard to, it's a lot of stuff to go through, get each of the details correct. Alright, well, I can't really fix it, but attempt to fix it. No, it's an opposing, sorry, yeah, my bad. I should have left it the way it was. It's an opposing force. So they have the same polarization as the magnet that created them. So, my bad. But the point is when the electrons are moved, they're expelling, when they do this movement, a force perpendicular to their movement. And it has to be, it has to be a black force. So somewhere I've made some mistake somewhere. Oh, that's right, it's the reflections. I'm sorry. It doesn't create a force. All it's doing is creating more reflectivity. So again, remember, the more concentrated the electrons are, the more likely that if there's something a black force hits, that it's going to reflect back. And it's the reflections that are essentially causing the repulsion between the two elements. So it's not really creating a force, it's just creating the capacity to reflect what comes at it. So that's the key ingredient. And that's only possible while you are compressing and releasing the pressure. So if there's no place, so in most conductors that can create its own short, because you're essentially creating a battery in the middle of a conductor. So this effect could be visualized better if you store the energy that comes out of it, when you move the magnet, in a battery or something. Because if you don't, it's just going to recycle the pressure back around the battery, back around the conductor. It'll just create an opposite current to balance the pressure. So, so that's the point I wanted to make, right? I think so. Yeah. So the current can't be stable in a conductor. You can't store voltage in a wire. So you can't just create a wire and then store a voltage inside of the wire permanently, because the wire will attempt to rebalance the pressure. So when you build up the pressure on this surface, the rest of the material will try to rebalance the pressure and put back supply the electrons to the now lonelier protons, and likewise rebalance the pressure of the protons. Okay, I think that's generally speaking okay. So anyway, the point of the video is really just to point out how the mathematics is really about these rays, and recognizing that they essentially create the inverse square law. So just like a light bulb radiating photons, it's the same rule. The light gets 4 times weaker half the distance. The same rules apply. The magnet's doing the same thing. It's radiating rays of magnetism. There are no real anythings moving around the magnet. And so if anybody has any evidence demonstrating that there's anything moving around the magnet, that's what I'd be interested in seeing, if there's anything to refute the fact that there really isn't. And the only thing these lines are used for in mostly examples of charge, but it is used. They use these artificial topography lines to essentially represent the inverse square law in a more visual way. So they're essentially representing the divergence rule as stated. Somewhere in here we got enough empty space. So again, they're just representing this fact with lines to indicate the strength of the force at certain distances. So the radial lines are a synthetic of the mathematics. It's just recognizing that it's a radial force. And yeah, so that's enough of that. Alright, so I think that's covers it. So anybody have any evidence disputing the fact that there is no evidence of anything moving inside a magnet? It's purely just a filter. It's just filtering external force. It's not creating any energy of its own. It's just reflecting or manipulating, bending force that comes into it. And that's all it's doing when it creates another magnet in a paramagnetic material. It's just doing the same. It's causing a similar effect in terms of it's making the conductor into a filter. And yeah, so I think that's enough. And such. So again, there's just so many people who think there's all kinds of motion, ether theories and all kinds of theories, and even the conventional model has some notion of it, right-hand rules and stuff, like there's actual real motion, when there really isn't. There's just creating polarization. And yes, polarization has a direction, but there's no motion except for the movement of the electrons by the force, the pressurizing of them.